In this lesson, we'll talk about real number system, set builder, and interval notation. First, let's recall all the major sets that we've been working with. What is a set? Set is a collection of objects, usually numbers, called elements or members, that will have a common property or properties. So set is just a collection of certain elements with the desired property. And we know a lot of sets already. The first set that we've been working with is set of natural numbers, like 1, 2, 3, and so on. If we add 0 to this set, we get a set of whole numbers. Within the set of whole numbers, we can perform addition and multiplication, but we can't perform subtraction. For example, 2 minus 3 is negative 1. So if we want to have a set where subtraction will be doable, we need to extend this set of whole numbers by some negative numbers, like negative 1, negative 2, negative 3, so the same as natural numbers but with negative sign in front. This kind of set is called set of integers. And among integers, we can already perform addition, subtraction, and multiplication. But we still can't perform division. For example, 2 divided by 3 is a fraction. So in order to be able to perform division, we need to extend this set by adding all possible fractions, either common fractions or decimal fractions. Such a set will be called set of rational numbers. And that's great. In set of rational numbers, we can already perform all 4 operations. However, those are not all numbers that we can find on the number line. There are some other numbers that can't be expressed as fractions. For example, a number pi, it has infinitely many digits after dot, root 3, root 2, root 5, root of any prime number. Those are the irrational numbers. The set of irrational numbers is disjoint from the set of rational numbers, but together they fulfill the number line. That means those are all possible real numbers. A set can be represented by using roster notation or Setbuilder notation. Roster notation means that we are listing all the elements of the set within the braces like this. Those elements will be separated by commas. However, roster notation we'll use only when we have limited number of elements to list. For example, to represent a finite set, like this one, here we list 3 elements of the set, 1, 2, and 3. So that's a set composed of 3 numbers. We could also use roster notation when we want to represent infinite set, but this infinite set has specific pattern that is easy to discover and follow. For example, the set of all natural numbers, marked by double stroke capital N, like this. That's a set of natural numbers, sometimes called counting numbers. We can list some of those elements. Usually we list the first couple elements, like 1, 2, 3, and then after comma write 3 dots. That indicate that the numbers follow that pattern. We skip by 1, and we can count like this as far as we want to. It goes up to infinity. So that's an example of an infinite set, but still represented using roster notation. The next set that we talked about, it was the set of whole numbers, which is composed of natural numbers and 0. The set of whole numbers will be marked by double stroke capital W, and we can still list those elements 0, 1, 2, 3, and so on. Then, if we add to the whole numbers negative integers, we produce a set that is called integers, and this set will be marked by double stroke capital Z. So here you can see the 2 representations using roster notation. We can start with 0 and go to the right 1, 2, and so on with 3 dots, and then to the left negative 1, negative 2, and so on with 3 dots. But this is maybe not so convenient to write. So we can use more concise notation and then record in those braces 0 and then plus minus 1, plus minus 2. So this plus minus is a shorter way of recording 2 numbers, plus 1 and minus 1, at the same time. So 0 plus minus 1 plus minus 2 and so on. That represents all integers. You may wonder why we use a letter Z rather than I for integers? Well, originally mathematicians start using letter Z because of the German word Zahlen that represents integers. So we have capital N that represents natural numbers, W that represents whole numbers, and Z that represents integers. Let's introduce more terminology and notation. If we want to indicate that certain number is an element of certain set, for example, if we want to say that 5 is an element of the set of natural numbers, then we use this unfinished E sign. So this sign tells me that 5 is an element of the set of natural numbers. To indicate that a number is not an element, we are crossing out this unfinished E sign. So here we say -1 is not an element of the set of natural numbers. To denote the empty, or sometimes it's called null set, we use this crossed out circle or just empty braces. Since the empty set does not contain any elements, that's why nothing is listed within those braces. The first sign is used more often than the second one, so that's the sign for an empty set. Okay, now we should be ready to talk about the other representation of sets. It's called Setbuilder Notation. Remember, roster notation was used only when we have finite set, just a few numbers to list, or when we have infinite set, but with specific pattern that is easy to follow. However, if we want to represent any possible set with particular properties, it's a lot better to use Setbuilder notation. What is it? Well, in Setbuilder notation, we focus on the property that the elements of the set supposed to satisfy. It could be one property or a few properties. How do we build a set using properties? Well, we still use those braces to indicate that we're talking about a set. Then we list what kind of general set we're picking elements from. Then there is a bar, vertical bar like that, that is read such that, and then we'll list what kind of property our element's supposed to satisfy. So here we can list one property or using commas a few properties. So the general structure of how to read the set given in a Setbuilder notation is as follows. We read the set of all elements x from the set S such that the x has a given property p. This first letter, it doesn't have to be called x. We can use some other letters, for example n or y or t, it doesn't matter. Usually if we talk about natural numbers or integers, we use n, and if we talk about some other numbers, real numbers, we usually use x. Let's see some examples of Setbuilder notation in practice. In the first example, we want to represent all rational numbers. Well, let's recall that rational numbers are all fractions. And if the fraction is in the form of a decimal, it is either a finite decimal or infinite, but then repeating. So rational numbers do not contain infinite but not repeating decimals. If it is infinite, it must repeat to be a fraction. Okay, so how can we represent rational numbers using Setbuilder notation? First of all, rational numbers are marked by capital Q, double stroke Q, and the definition of it is this is a set of all fractions. So we could, for example, write P over Q, which is a fraction, such that both numbers P and Q are from integers, and the bottom number Q is never zero. So we have all possible fractions. Another example, irrational numbers. Remember, irrational numbers are the ones that are not rational. That means the ones that can't be expressed as fractions. For example, any infinite but non-repeating decimal, and a root of a prime number, some famous mathematical constants like pi or e. So the set of irrational numbers is marked by IQ, and using Setbuilder notation we can say those are all real numbers x such that x is not an element of rational. So as you see, this really states any number that is not rational is irrational. Notice that if I would like to follow exactly this way of writing Setbuilder notation, I could write all x's from real numbers such that x is not a rational number. However, customary, if the elements that we are talking about are from real numbers, we don't necessarily have to write this set. We can skip this little step here, and if it's written just x such that we assume that the x is really real. Let's see another example. Here we want to represent negative integers. So how can we do that? First of all, the set of negative integers can be marked as double stroke z with subindex negative. And then we say this is set of all real numbers such that my number is really an integer and my number is smaller than 0. Okay, that's one way of representing negative integers. However, instead of writing this property that x is actually from integers, we can state this in the beginning, like the structure of Setbuilder notation suggests. So this could be written as the set of all integers, such that my integer is smaller than 0, that means negative. And another example, the set of all real numbers. Well, the set of all real numbers is our whole universe. We are working only within the set in our course. So if we think about set of all real numbers, we don't need to list any property, because those are all real numbers that do not have to satisfy any particular property anymore. Obviously, this double stroke capital R is a shorter notation than the Setbuilder notation. So quite often we will just use those special capital letters to indicate the major sets that I mentioned before. So natural numbers, whole numbers, integers, rational, irrational, and real numbers. How to see real numbers? Well, those are all possible numbers on the number line. So if we have a number line, every point corresponds to certain real number. And those numbers could be also referred to as coordinates. For example, on the number line, if we have 0 marked somewhere here and maybe 1 somewhere over there, then all other numbers fall in place. For example, here it's 2 and 3, and to the left we have equally spaced -1, -2, and so on. If we want to place some fractions, for example 1/2, it will be half away between 0 and 1, so somewhere there. And all other fractions we place correspondingly. And number pi will be approximately here, about 3/14, so that will be about pi. So every single point on this number line corresponds to a certain real number, and this number will be called coordinate of this point. Okay, so we know the rational numbers. Those are all fractions. That's why the set of rational numbers is denoted by capital Q. And why Q? Well, because fractions are quotients. Q for quotients. Okay, therefore to show that certain number is really rational, we need to be able to express this number as a fraction. So how can we express a number 1.5? Repeated, this little dash above 5 denotes the fact that 5 repeats forever. So this number looks like 1.555 and 3 dots. 5 is repeated forever. How can we show this number as a fraction? Well, here's the method. Let's call this number a. And then we are going to use this equation to produce new equations. For example, we could multiply this equation by 10, producing equivalent equation 10a equals, and multiplying by 10 causes that this decimal dot will be moved one place value to the right. So the decimal dot will be after the repeating sequence. Okay, we'll have 15 point and then 5, 5, 5 forever. Now let's rewrite original equation underneath. That was a equals 1.555 forever. And consider these two equations. If we subtract side by side these two equations, then we have 10a minus a is 9a. And on the right, we can take advantage of this ending after the decimal dot, both of those fractional parts after decimal dots are exactly the same. So when we subtract those numbers, the fractional part will actually cancel. So what's left is 15 minus 1, which is 14. The 555 forever will be gone. So that's great. We end up with 9a equals 14, which can be solved for a just by dividing by 9. Divide the whole equation by 9. The 9 goes to the denominator, and we see a beautiful fraction, 14 over 9. So yes, a is a rational number because we know how to express it in fraction form. And what's a? Well, a was originally 1.5 repeated. So we just proved that 1.5 repeated is a rational number. Okay, let's see how can we deal with the second example. This time the repeated sequence is 41. We stay with 0.23 and then 41 will be repeated. Okay, to see it better, we can write it as 0.23 and then 41, 41, 41 is repeated. Similarly as before, we can call the original number as, for example, a or x or any other letter that you wish. And the idea is to produce two equations like we did in previous example. But what we want to make sure is that in both equations the tail, the fractional part after decimal dot, will be exactly the same. So the idea is to move the decimal dot after the repeating sequence and before the repeating sequence. So whatever is after the dot will look exactly the same. Okay, I would suggest to start with the larger number first. So first let's move the decimal dot after the 41, meaning I need to move decimal dot 4 places, so I need to multiply the original equation by 1 and 4 zeros, 10,000. Therefore, if this number is called a, my first equation will be 10,000a equals, and this dot travels here, so it's 2, 3, 4, 1, point, and 41 is repeated. I don't need to list those numbers so many times anymore. I can use the bar over the repeating sequence. Now, to produce the second equation, I'm going to multiply by just 2 places, so by 100. And then I will have 100a equals 23, and then after decimal dot I still have 41 repeated all the time. So now I have the system of two equations to deal with. Okay, similarly as in the previous example, I'm going to subtract those equations side by side. So 10,000 minus 100 is 9,900a. And here the top number minus the bottom number, the fractional part will cancel each other, and 2341 minus 23 is 2318. Okay, so that's nearly the end. We just need to divide the equation by the leading coefficient 9900, and we present a as a fractional number, 2318 over 9900. Now we could do one more thing. We could reduce this fraction to the lowest terms, leaving us with 1159 over 4950. But even at that stage, we already proved that 0.2341 repeated is a rational number. That's a rational number because it can be expressed as a fraction. Well, you may practice a few more numbers from the book, or just come up with any repeated decimal and try to convert it to a fraction. Okay, let's review some more terminology. For example, if we talk about opposite or additive inverse, we are thinking about a number that differs from the original one just by placing a minus in front of it. So if I have a number 3, the opposite is negative 3. And the opposite for negative 2 is 2. Notice the properties of these two opposite numbers. When you add them up, 3 plus negative 3 is 0. Generally, a plus negative a is 0. While multiplicative inverse, which is also called reciprocal, is obtained by flipping the number, by reversing the numerator and denominator. So, for example, the reciprocal of 3 would be 1/3, and the reciprocal of negative 2/5 is negative 5/2. So here we do not change the sign. What we do change is numerator with denominator. They've got flipped. And if we multiply two reciprocals, two multiplicative inverses, we end up with 1. For example, 3 times 1/3 is 1. A times 1 over A is 1. The next concept is absolute value. Absolute value is a distance of a number from 0. Since distance is always positive, absolute value is also always positive. And the formal definition of absolute value goes as follows. Absolute value of A is either the same A if the A was positive, or 0, or it is opposite to it if the original A was negative. This is because we want to leave the absolute value of something always positive. Okay, let's see how this works on some examples. Absolute value of 2 is equal to 2. Why? Well, because if A is 2, A is positive, so we follow that rule. The answer is the same A, so it's 2. However, absolute value of negative 2, since negative 2 is below 0, so we follow that statement. The answer, according to our definition, should be negative original A, but that was A. So it's negative in a bracket, whatever we had originally, negative 2. And two negatives makes it positive, so yes, we end up with positive. So the definition really works. Okay, let's practice a bit. We need to evaluate this expression. According to order of operations, we're supposed to evaluate absolute value first. So let's copy the first minus, and then instead of absolute value of negative 5, we have 5. Therefore, the overall answer is negative 5. Second example. Again, let's perform the operations within the absolute value sign, which is a grouping sign. 2 minus 6 is negative 4, so the first statement could be written as absolute value of negative 4. Then copy the minus and then replace the absolute value of negative 7. Oh, that's exactly 7. So we subtract 7, copy another minus, and absolute value of 2 is 2. And the next step, release the absolute value sign. So absolute value of negative 4 is 4. And then we subtract 7 and subtract 2. That would be 4 minus 7 is negative 3. Remember, when we deal with subtraction, we go from the left to the right. So this subtraction needs to be performed first, and then copy negative 2. So overall, we have negative 3, negative 2 is negative 5. Okay, let's try to compare numbers by using the inequalities. Those are strong inequalities, and those are weak inequalities because they include the equal sign, or just an equal. If we have these two numbers, which sign should we place? Negative 5, negative 7. Okay, if we imagine number line, negative 7 is more to the left than negative 5. So negative 5 is larger. Okay, we place this sign. Negative 5 is larger than negative 7. Now, if we need to compare absolute value of 7 and absolute value of negative 7, well, since absolute value of negative 7 is actually the same as 7, and absolute value of 7 is the same as 7, then we should place an equal sign. These two are equal. Next, to compare these two expressions, absolute value of negative 5 is just 5. And here we have a negative, and absolute value of 5 is 5. Okay, negative 5 is definitely smaller than 5, so we use this inequality. Over there, we have negative absolute value of 0, which essentially is 0, and absolute value of negative 0, which still is 0. So these two are equal. The next example is a little bit more interesting, so maybe try to pause the video and try the next two examples by yourself. Okay, let's analyze the situation. Absolute value of something. Well, absolute value of something is always positive or 0, so this number has to be positive. However, that number x, well, it can be positive or negative. If x is positive, then absolute value of x doesn't change it. So in case of positive x's, we'll have equal sign. However, if x is negative, then the absolute value of it is always positive, but the x originally was negative. Okay, so in this situation, the right-hand side is smaller than the left-hand side. Therefore, we should use this sign. The absolute value of x is bigger or equal x. And finally, the last example. Well, absolute value of anything is always bigger or equal 0. Can this right side be equal to 0? Yes, if x is 0. But if x is anything else than 0, the right-hand side will be bigger than 0. So overall, we use the smaller equal sign. 0 is smaller or equal than absolute value of negative x. Now let's look at interval notation. We need to complete this table with 3 columns. In the first column we have Setbuilder notation that should correspond to the graph and correspond to interval notation. What's an interval? An interval is a section of a number line between two given points. For example, if we have a set of all real numbers such that our numbers are larger than 2, to picture out this set, we mark the important number 2 somewhere here. However, we mark it with open circle, with hollow circle like this, just because the 2 is not taken, because we don't have the equal sign. So that will be number 2, and now we're talking about all numbers that are larger than 2. So we mark it above the number line like this with arrow to the right, and we can shade this set. So this is a graph of set of all numbers larger than 2. How do we write this in interval notation? Well, the structure of interval notation is we open brackets, either round or square. Round bracket corresponds to hollow circle. That tells us we do not include the endpoint. No endpoint. Or square bracket if we do include the endpoint. So with endpoint. And that corresponds to the covered circle, filled in circle. Okay, so we start with a bracket, then we put a comma, and then we end with a bracket. Again, it could be a round bracket or a square bracket. The round bracket corresponds to the strong inequality, either like this or like that. The square bracket and the filled in circle corresponds to the weak inequality, either like this or like that. The weak inequality includes equation. So let's try to record this set using interval notation. We have a hollow circle. We do not include number 2 in our set, so we use round bracket. And we need to start with 2 and end at infinity. So the starting point is 2, then comma, and the finite point, well, it doesn't exist, so what we do, we use infinity. That tells us those numbers are going forever, will never end. Infinity will always have to have a round bracket because we don't include the endpoint. There isn't any endpoint there at all. So remember, infinity will always take round bracket. Okay, second example. Let's read this set first. We're talking about all real numbers such that those numbers are smaller or equal -2. Okay, our important number is -2. Let's place it somewhere on the number line. But at this moment, I need to ask myself, okay, should I use the hollow circle or the filled-in circle? Since I have equal sign, then the -2 is actually included in the set. So I should use the filled-in circle. Let's place it somewhere there. Filled-in circle that represents number -2. And then we're talking about all numbers that are smaller or equal than -2. So it goes to the left. Smaller numbers are going to the left, larger to the right. So that's our set. Okay, when we produce interval notation, we start from the left. So we don't actually see the first point, but this is the negative infinity. So treat it like a point. Again, we use round bracket because of infinity, and we need to indicate negative. For positive infinity, we don't need to write plus, it is assumed it's positive, but if we think about negative infinity, it must be indicated by a negative sign. Then comma, and then we list the final point, which is -2. Since the -2 is taken, we are using square bracket this time. So interval means we need to state the first and the last point, and it is assumed that all numbers between these 2 points, including infinity sign, all those numbers belongs to this particular set, which means that interval is used when you can't really list your numbers because there's so many of them. Okay, in the next example, the Setbuilder notation tells us we're talking about all real numbers that will oscillate between -1 and 2. X is larger equal than -1 but smaller equal than 2 at the same time. So those are the 2 important points to mark on the number line. Since the inequalities include equation, I need to use filled-in dots to represent -1, let's say it's here, and 2, for example here. And the x's, the numbers that belong to the set, oscillate between these 2 points. That means that's our set. To state it in interval notation, we use square brackets, and we start our numbers from -1, comma, we end our numbers on 2, square bracket. All the numbers in between will be taken, so we're unable to list them because there's infinitely many of them. It's not only about integers, it's about all real numbers that are within these 2 brackets. That's why it's convenient to use the interval notation. Okay, in the next example, we have given the graph of the set that we have in mind. This graph goes from -3 until 5, with -3, but without 5 because we have hollow circle. Well, let's give the interval notation corresponding to this set first. When you do that, it's a good idea to keep in mind the rule from the left to the right. You swipe your number line from the left to the right, and whatever comes first, you write first. So we start with -3, comma, and we go until 5. What are the brackets? Well, this is filled-in circle, so it's a square bracket, and this is hollow circle, so it's a round bracket. Interval from -3 to 5. Okay, let's give the corresponding Setbuilder notation. So we open a set bracket. Then we state all real x's such that, and what do we require from our x's to be? Well, the x must oscillate between -3 with the endpoint, so equation is included, until 5 without 5, so no equation here, and complete the bracket. Next example, here we have half a line starting from 1 and going forever to the right. So the corresponding interval would start with 1, and since we have hollow dot, it will be round circle, 1, comma, and goes until infinity, round bracket. The corresponding Setbuilder notation, okay, let's start with the bracket again, all real x's, such that my x is larger than 1, strongly larger than 1, because we have hollow circle here. And the following example, now we have given interval notation, we need to graph it. Okay, let's place these 2 numbers, -6, it will be hollow circle because it's a round bracket, until 7, let's say somewhere here. Again, round bracket, hollow circle. Everything what's in between. And I'm sure you can give the Setbuilder notation that corresponds to this set on your own. It will be a set of all real x's such that the x is between -6 and 7. So we can write like this. X is enclosed from the left by -6 and from the right by 7. Complete the bracket. When you write your compound inequalities in one row, make sure that all of these inequalities are really going in the same direction. So all of them should go that way. For example, writing like this, x is larger than -6 and then smaller than 7 doesn't make sense. avoid this kind of problems with notation. Why it doesn't make sense? Because here we're just stating that x is larger than -6, and over there we're stating that -6 is smaller than 7, which is obvious. It doesn't say anything about x. We can't conclude that x is smaller than 7 from writing like this. Basically, x is too far from the 7 to make any claim. For example, we could have an x equals 8 that would satisfy this inequality, and obviously this inequality is always satisfied. However, 8 is not in our set, so this kind of writing doesn't work. Please avoid it. And the easiest way to avoid it is to make sure that your inequalities go in the same direction and the x is in between the two numbers, because your x is an unknown number that oscillates between -6 and 7, so it should be written somewhere in between, not outside of these two numbers. Finally, this diagram tells us that we're talking about all numbers on the number line. So in interval notation, I could denote it by opening round bracket going from -infinity, comma, until +infinity, and close the round bracket. In Setbuilder notation, well, we could actually use this capital R letter because it's the most concise way of representing the set of real numbers. So there's no need to write something like this. It's kind of artificial. It still means set of real numbers, but I would prefer if you write just capital R here. Okay, let's talk about order on the number line. Well, assume that we have these particular numbers to match with the points A, B, C, D, and E on the number line. How do we know where to place those numbers? Well, since on this number line the arrow is going to the right, we know that point A corresponds to the lowest number and point E to the highest. So A would have to correspond to which one? Oh, -pi, because that's approximately -3.14. So A would be the same as -pi. Then a number that is a little bit higher than -pi is -2. So -2 will be placed where B is. And then we have positive numbers, 3, 5, and pi. So the highest number out of 3, 5, and pi is 5. Therefore, 5 should correspond to E. And then we need to compare 3 with pi. Since pi is about 314, so it's a bit higher than 3. Therefore, 3 will correspond to C, and pi will correspond to D. So that wasn't too difficult. Now let's make some observations. The numbers on the number line are getting larger and larger towards the right. And the arrow on the number line indicates the increasing order of numbers on the number line. So the arrow doesn't really tell us that the number is proceeding, is going and going forever. We know that. The line is proceeding forever in both directions, so we don't need to state this. However, the arrow is actually giving us direction in which the numbers are increasing, so the order on the number line. How do we find distance between any two given numbers on the number line? For example, if we have 5 and 8, well, we could locate 5 and 8 and just count how many steps is from 5 to 8. From 5 to 6 to 7 and to 8. 3 steps. How do we get those 3 steps? Just by using 5 and 8. Well, we start from a larger number and we subtract the smaller number. So 8 minus 5 gives us the distance 3. 5 and 8 are at the distance 3 steps from each other on the number line. It's already a little bit harder to figure out how many steps is -7 from -11, but still we can place those numbers on the number line, and we know that -7 is closer to 0 than -11, so -11 is more to the left, and -7 is somewhere there. And then we can follow the same strategy as before. Take the larger number, which means -7, and subtract the smaller number, which is -11. Okay, since we have two negatives here, that converts into addition problem. So we have -7 plus 11, oh, that's 4. Therefore, -7 is 4 steps away from -11. This distance is 4 steps. Okay, that's fine. But what if we have two numbers a and b, and we have no idea if a is smaller than b or the other way around? For example, b could be smaller than a. So to find the distance between a and b, if b is larger than a, we'll just follow the rule larger number, which is b, minus the smaller number, which is a. That's great. But what if b and a is positioned that way? Oh, then we'll have to go a minus b. Good. But what if we want to have one expression, not two expressions, depending on the case? We actually have the expression that will give us this distance between point A and B on the number line, no matter what A and B is. This will be absolute value of the difference A minus B, or B minus A. Doesn't matter what you use here, but as soon as you put absolute value, you actually cover both cases. So absolute value of A minus B gives us the distance from A to b. And we don't have to worry which number is larger. For example, if I will write absolute value of x minus 1, that tells me the distance of a number x from 1. How far is x from 1? And if I will say, okay, for example, this is equal to 2, I have in mind such a number that is 2 steps away from number 1 on the number line. So 1 works like a center, and then I go 2 steps forward, making it 3, plus 2 steps, or 2 steps backwards, making it -1. Therefore, my x can be either -1 or 3, and it will satisfy this equation. So that's a great geometrical interpretation that will help us to solve, without even using any algebra, equations with absolute value like this, just by interpreting absolute value as a distance between the two quantities. So 3 is at the distance 2 from 1, and -1 is at the distance 2 from 1. Therefore, x could be equal to -1 or 3. And the last example that I want to show you is an application problem. We have a diagram that represents company profits and losses during certain years. The vertical scale is in thousands of dollars. So a number 77 tells us that in this particular year, 2010, the company's profit was $77,000. Okay, now we need to answer the question, the total profit or loss for the years 2007 through 2010. So all those years. To find total profit or loss, what we need to do is add all losses and profits from the 4 years. Therefore, just use operations on integers. Okay, it will be -142. Then we add -225 and add -185 and finally add 77. So let's use calculator. This would turn out to be -475, which means that over those 4 years, the company lost $475,000. In point B, we are asked to find the average profit or loss per year for the years 2007 to 2010. So we're talking about the same 4 years. Average profit or loss means that we need to distribute this overall loss over 4 years, meaning that we need to divide the loss by 4 years to get the average. And again, using calculator, we end up with -118.75. So on average, the company lost approximately $119,000 per year. Now let's find the difference between the profit or loss in 2010 and that in 2009. So this time we need to compare the results in these two consecutive years. The difference between the result in 2010, meaning we need to start with 2010, $77,000, and subtract the result in 2009. So we're subtracting negative number. Here we need to be careful with double sign again. So this is really 77 plus 185, which makes it $262,000. The difference between the result in 2010 and 2009 is actually as far as this much, which is $262,000. So the company improved over those years by $262,000. Finally, we need to find the difference between the profit or loss in 2008 and 2007, which means between these 2 years. Okay, we start with the last year and we subtract whatever the result was in the first year. So negative 225, subtract the result, so make sure to open the bracket, negative 142, which equals minus 225 plus 142. Using a calculator, that becomes negative $83,000. What does it mean? Well, that means that the company performance worsened. It lost $83,000 from 2007 to 2008.